This is Mr. Craig, and this is examples part 2 for the Kinetics, the first day lecture. What I want to talk about in examples part 2 is what type of question you will see on the AP exam and what type of question you'll see on the test. In this example here, or this set of examples, we have an experiment where we have the reactants A, B that form C and D. Now, honestly, we don't even need to see this balanced equation to do these types of problems. And often, what I don't want you to do is look at it and say, oh wow, look at that number 2 there. That 2 must mean that there's something really special that's going to take place here. Ignore. If you ever see a balanced equation and a table that looks like this, I would cross that equation out. I wouldn't even look at it. Oftentimes, some people, and we're going to talk about the orders of reactants here in a moment, some people might look at that and say, oh, that's first, or that's a second order reactant. I don't want you to make that mistake. Alright, so looking at the table here, which is very important, the experiment 1 through 5, right here, these deal with the different trials. In other words, you'll notice that the concentrations for A are here, and the concentrations for B are in this third column. Now notice that there's no coefficient in front of the concentration of B. We don't care. The balanced equation is to make sure that the number of atoms are the same on both sides. What you will recognize is that in some cases I may leave the concentrations the same in a couple trials. Like in this case for A, I have 2 and 5 are the same, and then for B I have 1 and 2 are the same. This is kind of important. If you're designing a lab, you want to try to have concentrations remain the same while changing other concentrations so that you can find out, ooh, this reaction is really fast if I double it, or it doesn't change when I double it, or it becomes really, really fast when I double it. And again, this is all determined experimentally. In this last column, we have the rates, and again, the initial rate. And the rate in this case is molarity per unit of time, which happens to be second. So molarity per second. We will use this data in part 3, or something that looks like this in part 3, to determine the rate law. And the rate law will be explained here in a second. I'm going to scoot down here to the orders. When we talk about a reactant, it's either a zero-order reactant, a first-order reactant, or a second-order reactant. Now, for the AP exam, those are the only 3 orders that we care for a reactant. And what that means is, if you're looking at a zero-order reactant, okay, and that's right here, what that's saying is, regardless of what the concentration is, the rate of the reaction does not change. So if I go and double the concentration, the rate remains the same. If I triple the concentration, the rate remains the same. That's for zero-order reactants. If I'm looking at a first-order reactant, which is right here, if I double the concentration for a first-order reactant, then I speed the reaction up twice as fast. If I triple the concentration for a first-order reactant, the reaction is now 3 times faster. If I quadruple the concentration, it's now 4 times faster. That is a first-order reactant. So again, zero order, you change the concentration, whether it goes up or whether it goes down. That rate remains constant. For a second-order reactant, what happens is if I double the concentration, this is an exponential growth. So if I double it, it's 4 times faster. If I triple it, it's now 9 times faster. If I quadruple it, it's now 16 times faster. So when we are looking at doing these labs or looking at this data here, we're going to find out what each of these reactants do and how they behave. Some are first order, some are zero order, some are second order. It can only be one of those 3. Now, I can have A be a first order reactant and B be a second order reactant, and that's fine, just as long as they have an order. Okay. And then down here I have how you would represent that. If we're looking at, say, a first order reactant, you have the option of putting a 0 as your superscript or not showing it at all. Because anything to the 0 power is 1. So if you have a concentration that's a zero order reactant, and when we go and plug it into the data that we're going to be using for this table here, it doesn't change. If I look at a first order reactant, you have the option of leaving it as it's noted there, or you could put a little 1 as a superscript there. However, with the second order reactant, we must show the exponent as a 2. Okay, and that'll become more clear once we actually do the examples in part 3. On the back side of this sheet, I actually have what we're going to do in examples part 3, so if you want to look over that, that's fine. However, I'm going to actually go through this whole sheet when I do an example lab. So I don't really want to read it to you because it doesn't make a whole lot of sense unless you've actually done it. Now, I do want to talk about the rate law. The rate law is something that's very important that you'll always be asked if you have a kinetics type question here. And what this rate law looks like is an equation that actually has rate to start it off. So the rate law must have the word rate within it. And the rate deals with the rate down here. So we're going to, in the examples part 3, you will pick one of these rates to determine what the K is. And the K is a constant. And the K is a constant for all these trials. Now, what's also cool is once we determine the order, and I have M and N here, you can use X and Y, or you can use whatever letters you want. Just don't try to use O or L, things that look like numbers. Why I use M and N, it's what my high school teacher taught me, and that's what my college professor used. I don't think there's any logic as to why. It's just something that's been taught to me. So the rate law will include the word rate. It'll have the constant for the reaction, and then it'll have the order for each of the reactants. Notice there's no products in this. We do not care about the products when we're doing kinetics. We only care about the rate of disappearance when we're doing these types of calculations. Alright, move on to the next video, and I'll actually work out a problem or two here.